Hello everybody, and welcome to An Ocean Full of Possibilities, a story about a quest for polymers from CO2. My name is Eric Schuler, and I'm a PhD candidate at the University of Amsterdam. I'm grateful to be able to talk at the Green Chemistry and Engineering Conference, which this year happens online and unfortunately not in Seattle, but I want to thank the organizers for still making this possible. The ocean I want to talk about today is actually a consortium. The Ocean Consortium includes 9 partners from a diverse background, from industry, university, and research institute. And it's funded by the EU Commission in a Horizon 2020 program. In the Ocean program, we aim to make sustainable polymers from CO2. We start with CO2, which we electrochemically convert into formate, which we then couple to oxalate. Oxalate is electrochemically acidified to oxalic acid, from which we obtain the monomers to make new polymers from. On the right-hand side, you can see an example of such a polymer film. A strong emphasis in the program is the electrochemical conversion of CO2 and oxalate and the integration of all the steps into one consecutive process. Our mission for that process is to make it sustainable by meeting the 12 green or circular chemistry principles. We have a especially strong focus on reaching overall negative CO2 emissions, make the process scalable to large applications and easy to integrate into existing processes, and of course, to make a good business case and make it economically viable. But how did we get here? As this year's theme of GCandE is systems-inspired design, I want to take the chance to explain you how we use design thinking and systems-inspired design to design the overall ocean process. To design a process, we first have to think of what it requires to make a process in the end successful. The first part is that the new process should solve a problem or many problems, and by doing so avoid to create new problems. Secondly, as a principle of design thinking, the process has to consider the needs of all the parties included, starting from the product side to the feedstock side. And thirdly, the process should be sustainable. That means it should be economically sustainable, but also environmentally sustainable and socially sustainable. These 3 principles I want to use as an outline for my presentation, and here why I want to start with the problem-solving part. For that, I want to go from the feedstock side all the way to the product side. So let's start with CO2. We have way too much CO2 in our atmosphere, and we humans are very good at emitting it. This CO2 in the atmosphere causes the global temperature rise through the greenhouse effect, which in turn causes climate change, which is ever more so present now and a big problem in the view of the public, and especially in the younger generation. So which solutions can we provide? Well, we have to reduce emissions, and that we can do by stopping activities, such as flying to conferences in Seattle. Alternatively, we can also change the behavior and change processes. So we would do the conferences not in Seattle anymore, but on the internet, as we're doing it now. Or we take a train to a conference which runs on electricity and doesn't use fossil carbon. Thirdly, if we still want to fly to Seattle, what we can do is we can capture the emitted CO2 from the engine's exhaust. It's a bit difficult with planes, but it works very well on stationary systems such as cement plants. From there, we in the end get some surplus CO2. That surplus CO2 we also get from the second solution to the CO2 problem, which is capturing CO2 from the air. With our new feedstock, the surplus CO2 we captured, we can make several things. We can circulate it on one side and turn it back into fuels, or we can turn it into materials, which are single use, for example. Materials we can also make that it last longer and are therefore storing the CO2 for a long time. This storage can also be achieved by pumping CO2 underground in carbon capture and storage. To make materials from CO2, we have 2 options. We can on one hand side do mineralization to carbonates, which are used as building materials for long-term storage. And on the other hand side, we can make carbon-based materials such as polymers, where we can have single-use polymers for circulation or longer-term storage again, in the form of polymer-based building materials. During the process, we're also facing problems, and that is mainly the stability of CO2. If you look at the enthalpy diagram on the left here, you see that CO2 and water have the lowest energy. If you want to convert those into something useful, such as sugars, alkenes, or syngas, we have to invest a lot of energy. This is not easy, and there are many options available. What we are opting for is electrochemistry. With electrochemistry, we can reduce the fully oxidized CO2 again and turn it, for example, into formate in our case. Electrochemistry also has another advantage. We can solve another problem, and that is the storage problem of energy from renewable sources, which we now can use in our process to turn CO2 into renewable fuels or materials. Lastly, let's look at the product side. The current production of polymers and their use is quite problematic. We always start with fossil carbon in 99% of the cases, which we turn into monomers, and those we turn into polymers. From those polymers, we can make commodities such as plastic bottles. Plastic bottles are actually not even that bad because they can partly be recycled. However, most of the plastic in the end ends up in incineration plants, landfill, or the environment. From there, it causes problems such as microplastic pollution, CO2 in the atmosphere, or toxic chemicals which are in the environment. The main reasons for these practices is mainly price and cost. Fossil-based polymers are just much cheaper than any green alternative. The recycling rates are really low because recycling today needs a difficult infrastructure, and in the end, it's not infinitely possible anyways, so you will introduce fossil carbon into our hemisphere. And lastly, also the properties of renewable polymers don't quite always match the requirements we have for polymer applications today, so we really also have to work on that side. So ideally, we start with renewable carbon. This renewable carbon, for example, could be CO2. So we turn CO2 into monomers. Those monomers, again, we make new polymers from. Those polymers we turn into commodities, but we have a much higher recycling rate here now, both on the chemical and, more importantly, even on the mechanical recycling. Yet, still some of the polymers will end up in incineration, landfill, or the environment again. However, we should design them such that if they end up there, they should turn into benign chemicals or CO2. The CO2 here is not so problematic anymore because it can again be turned into monomers, so we also have a circular process existing there. To successfully implement such a system, we need to develop new polymers from renewable sources, which are also biodegradable. Also, we have to put the users into the center here to make sure that the new polymers are compatible with the current molding and extrusion equipment, which makes it easy for them to be adapted. And lastly, we have to come up with improved recycling routes where we can recycle the polymers at a higher level. To solve all these problems, we at Ocean have a 5-point strategy. The first point is that we want to address the critical elements hindering the implementation of new electrical processes on a commercial scale. Secondly, we think it's clever to target high-value products, such as polymers, for special applications to get a better business case for our process. Thirdly, we want to demonstrate and integrate the process under industrially relevant conditions to see where we really have to work on. Fourthly, we want to also lower the power costs. We can do that by combining the reduction of CO2 with an oxidation reaction on another half cell in the electrochemical process. And lastly, we want to use a trans-disciplinary approach for the introduction of advanced technologies. What does that mean? Well, we will work with different partners on developing the process. So in part 2, I will introduce to you all the partners which have come together in this trans-disciplinary approach to develop a new process. In the Ocean process, we have partners that represent users in all stages of the process. That means from the feedstock through the process and the product side. On the feedstock side, we have RWE. They're a large power producer in Germany. They run coal power plants and they have developed processes to strip the CO2 from their flue gases. On one of their sites, which you can see in the picture, we will install our pilot plant and test it there. Most partners are included in the process development itself, and here we work at different technological readiness levels. At universities, we develop new polymers and look into the reaction mechanisms of the reactions of the electrochemical part or the formate coupling, for example. In research institutes, this knowledge is used and combined with other reactions, so we try to make the process on an early bench scale. Lastly, we have the companies. At this stage, we use the work of the earlier stages and scale it up to a commercial scale. For now, we're going to pilot scale. That requires then also to automate all of these systems, which we have been using before, to run them for longer times and to integrate them into one consecutive system. And to make it complete, we have Avantium on the product side. They have been developing polymers before and worked with several big partners to introduce the polymers to the market. To in the end bring our process to the market, we develop a business case and we use life cycle assessment to get the numbers right on the costs we have. We have two partners at IIT and Avantium which look at the whole picture of the process. That means they put together all the singular processes, they look at the numbers there. That means they ask the partners for details of which kind of power consumption they have, what kind of reaction temperature they have, and their way they can virtually integrate the whole process. And even more so, they can identify where we still have problems and where the highest potentials for improvement are. So this is how we use systems-inspired design and design thinking to design the ocean process. In the second part of my talk, I want to show you how we keep on using the systems-inspired design and the collaboration throughout the project. And for that, I'll use the formate coupling step, which is one of the combining elements and which is what I'm working on. Formate coupling is a connecting process in the overall ocean scheme, and we turn formate into oxalate. We don't do this electrochemically in this case, but we use a thermochemical process. To make the overall process successful, it's really key to integrate the steps with each other. In my case, therefore, I have to talk at the feedstock side to the producers of the electrochemical compound, the formate. I have to know what the output of the electrochemical cell is in that case. Secondly, in the process, I am requiring heat. So I can also talk to the whole consortium and we can look if we can do heat integration at some point and save energy instead of running a heater. Thirdly, on the product side, of course I have to talk to the people which do the acidification of the oxalate I'm making to oxalic acid, and I have to know which requirements also the polymer producers have in the long term, or if I have to make changes to my process to fit their needs. Let me tell you a bit more about formate coupling. Formate coupling is a really old process. It's been developed before 1900 and you can see here a patent from 1902. It's also been used on a large commercial scale in the early days. It's been the way to make oxalic acid before the advent of oil. The reaction requires a solid reactant, the formate, and a base catalyst. They use high temperatures above 400 degrees. The reaction time is rather long, between 30 minutes to 6 hours, depending on the patent you read. You make a bunch of carbonate in a side reaction, which you have to get rid of, and it's all a batch process. We're not very satisfied with this so far, and that's why we formulated a mission to turn this into a continuous process, and we're aiming for much milder conditions. To make this mission successful, we face a challenge at different levels. On a molecular level, I believe we have to understand what's really going on in the reaction. That's why I'm studying the mechanism. Once I understood the mechanism and the crucial parameters from that, I can go to the reaction level and use the knowledge to find better catalysts for the reaction, which can then drop, for example, the reaction temperature. Also, I can really look into how to optimize the conditions which I learned about in the mechanism, and I can optimize them and understand their interactions with each other. In a third step then, on the process level, we can use this knowledge to design a new continuous reactor, build it, and test it in the end. To understand the formate coupling reaction, it is important to know which intermediates actually cause the coupling of the two formates. For that, I use operando Raman spectroscopy, where I can see the disappearance of the formate throughout the reaction, the appearance of an intermediate, and the formation of oxalate. You can see here the formate, and then there the oxalate, and in the middle we have the intermediates. However, We're still limited in resolution with the spectroscopy techniques, and that's why we went on to do molecular dynamic calculations. On the left, you can see in the first step how the carbonide ion, a double anion of carbon dioxide, is formed by the abstraction of the proton from the formate, which then, on the right, in the second step, attacks another formate to form the CC bond and release another hydride, so we get our catalyst back in this case. So we've learned that the carbonide ion is quite crucial in this reaction, and to form such species, we really need to have a strong base. So when we were looking for new and better catalysts, we of course went to look for strong bases. However, a lot of strong bases is really important to work really water-free because otherwise they degrade. We use so-called super bases, and with those we could achieve much higher oxalate yields compared to conventional bases we've tried also. In addition to that, we could significantly lower the reaction temperature. Overall, we could decrease the temperature by more than 200 degrees. We could reduce also the reaction time by more than tenfold. And lastly, what is really nice, we don't make any side reactions, so we don't have to have a separation step after the reaction here. In the next step of the reaction level, we're now looking into the conditions which we find crucial. What we want to find out basically is how these conditions interact and to which magnitude they influence the outcome of the reaction. For that, we're using design of experiments and then do response surface modeling. We include a magnitude of different reaction parameters, for example, temperature and time, but also things such as purging, the atmosphere, or the catalyst, just to name a few. What you can see here now is a response surface model we've been doing. We've been looking at temperature and time, and in the first step, we can basically see that the optimum for the reaction is on the top right. That means the real optimum might lay out of our tested reaction conditions. That's why we went on and expanded the area of interest here. So we did longer times and higher temperatures. In the third step, we finally got to a local optimum and hopefully a global optimum of this reaction. To estimate these global optima of the reaction conditions is really important in this step now where we design the reactor. So we really know which kind of conditions we have to tune the reactor for. We do the reactor design with Avancium and Hesitec because there the chemical engineers have experience in building such systems. On the right-hand side, you can see a reactor design already. We have in total 3 designs. This one is a bit blurred because of IP reasons. And what we're basically building is a new system which can run continuously. You can see the reactor there, where all the magic is going to happen, or basically it's already happening, and we're quite happy because it seems to work. Now, in the upcoming 2 years, we have time to optimize the systems and pick one of the 3 reactors for our overall process in the end. With this, I hope I could show you how you can benefit from using systems-inspired design and design thinking to develop a new process. On a horizontal level, we work from the feedstock to the product and consider all those needs. And we achieve that by using the vertical axis from a molecular level all the way to a process level. With this, I want to conclude my talk and thank my research groups. That's the Heterogeneous Catalysis and Sustainable Chemistry group with Professor Ravendran Chichu and the Industrial Sustainable Chemistry group with Professor Gert-Jan Grüter. Of course, I also want to thank my collaborators. That's at the University of Amsterdam, Dr. Bernd Ensing and Alberto Perez de Alba Ortiz, with whom I've worked on the molecular dynamics simulations for the formate coupling reaction. Then at the TU Delft, that's Professor Atsushi Urakawa and Dr. Atul Bansode, from whom I learned a lot about Raman spectroscopy. Lastly, I want to thank Professor Christopher Hardeker, Dr. Rebecca Taylor and Dr. Adam Greer from the University of Manchester, with whom I've done some interesting ionic liquid research for the formate coupling reaction. Then, of course, I also want to thank the European Commission for funding this research project. Lastly, I want to thank you for your kind attention. If you have any further questions regarding the Ocean program or the research on the formate coupling step we've been doing, please feel free to ask in the section afterwards or send me an email with your questions. Thank you.